Let's start today's lecture. Today's lecture is have the theme fiber orientation. You all know that fiber orientation is a very important phenomenon in the textile praxis, so that we want to analyze this problem more deeper. When we say orientation, we need to say what we mean under this term. We must say something about the fiber segment which we use for orientation, and then about the definition of direction, how to define the orientation vector. We can speak about very short fiber segments, extremely short, like here. Then the direction is without problem. It's evidently tangent of this small fiber segment. In other case, when we use this green segment having a longer length, we usually use the line from endpoints created from endpoints A and B. Yes, we will speak about the easiest case. It means we will speak about planar orientation of fibers. It's often a case, for example, of web and the other typical textile structures. Let we have some coordinate system x and y, and then we want to measure the directions from minus pi by 2 through 0 to plus pi by 2. Understandable. So from minus 90 degree through 0 to plus 90 degree. The easiest case is if our probability density function represents pure random, it means isotropic structure. So that in each case the direction is in the same probability. How must be this probability density function? Evidently it must be constant, isn't it? Yeah? If it is constant, we can write that such function, this function we call f0 psi 0 as our starting probability density function. This integral from this PDF f0 psi 0 d psi 0 from minus pi by 2 to plus by 2 must be equal 1, as every times integral from probability, each probability density function. But because this function is constant, we can write this one, so this one, and from this we obtain that such probability density function is constant and equal 1 by pi. Yeah, normally this isotropic structure is not real. Why? Usually, not every time, but usually, one direction is preferred. In the example of carding web, it's usually longitudinal direction. Yeah. Why the one direction is preferred? Because first, other segments are connected. Our segment are how to say it? Kick to this segment, yeah, through the process, because oriented it more to preferential direction. So it can be other segments or adjuncts from the same fiber or from the other fibers. And also, of course, the textile machine elements, different paints, cylinders, and so on and so on. In the reality, we obtain some structure with preferential direction. The real physical mechanism of this process is very, very complicated. It's very difficult to describe it. So that we need to use something which is more easy. easier. Therefore, we start with an idea. Let's imagine something like an imaginary flexible belt equipped with perpendicular spikes. Such spikes substitute the influence of surrounding of our fiber segment. This is shown here. Let's imagine such imaginary flexible belt having some spikes on, like a faker bat, yeah? And this substitute the influence of surrounding of our green fiber. On the end, our short fiber segment, sometimes I say fiber, but I mean a very short fiber segment, which is possible interpret as stride. On the end of our fiber segment, let's take some chalk, some orange chalk, and make on our imaginary belt an orange point. Okay, our fiber segment is lying on the straight line P. Evidently, end point of fiber is with coordinates x0, y0, so that tangent psi0 is x0 by y0, evidently. And now let's elongate our imaginary flexible belt. Please, our belt is imaginary, not real. And using this moving, the x coordinate, I must say, the fiber segment is slipping between the among the spikes, but it lie on our straight line P, so that after our elongation, after our moving, the situation is like on our picture here. X coordinates stay the same, y coordinate is higher. In the traditional spinning technology, we know the quantity drafting value, which is ratio. In our case, it means y by y0. Let's use this quantity as a degree of elongation of our imaginary belt. Well, if c is equal to 0, then if c is equal to 0, if c is equal to 1, then it is without elongation. Yeah, higher it is, so high is the elongation. Now from the picture we see that the tangent psi, angle psi is here, must be x0 by y. But y from this equation is c times y0, so that it is this one. x0 by y0 is tangent psi 0, so that this one. Now we can differentiate this equation, and after a few steps you can home to derive it. We obtain the such equation is here. This after rearranging, in final we obtain this equation. It will be important for us. Well, it was the discussion about one fiber. Now about all fibers. The starting probability density function, the starting situation was an isotropic structure, probability density function f0 psi 0. You know that the f0 psi 0 times d psi 0, probability density function times differential quantity, have some logical sense. It represents the relative frequency, but a little abnormal relative frequency. The relative frequency related to elemental class interval which is very, very short, differentially short. So we can imagine such elemental class, and relative frequency of such class is every times probability density function times differential quantity. Yeah, we will use this logical moment more times in our lecture. Well. So it is f0 psi 0 times d psi 0 relative frequency of fiber segments in the elementary class before drafting. After drafting, a new probability density function is coming. It is a probability density function f psi without zero subscripts. So that f psi d psi is relative frequency of fiber segments in the elementary class after our drafting of our imaginary belt. But both such relative frequencies must be same, because the fibers inside of starting angular elemental class must be same than after our elongation of our belt, imaginary belt, isn't it? Yeah. So therefore, it must valid f0 psi 0 d psi 0 relative frequency before drafting must be same that f psi d psi means the same after drafting. Using this equation, after substitution of our known expressions, we obtain the equation for probability density function of fiber short segments after using some drafting. It means after preferential of one, maybe longitudinal direction. How it is graphically on. So more are the fibers concentrated around we imagine longitudinal direction. Okay. Well, now only for your information, I don't want in detail to explain it. When you need to have some distribution function, please, here is the derivation of this. We can say in the moment that we can be very proud. We obtained quite new probability density function. Oh, how nice! We can publish it in a special journal of applied theory of probability. Sorry, no. This pictures show that the tangents of our angle psi have so-called Cauchy's distribution, so that it is one of a known distribution from theory of probability. Yeah? Okay, when you want, you can study it in more details. Sometimes is coming, or often is coming, the following problem. To this moment, our preferential direction was same than the y-axis, vertical axis. But sometimes preferential direction is another. We have y-axis here, x-axis here, and let's imagine the preferential direction is the direction of our blue arrow, which have two y-axis, some angle alpha. So we can write the angle psi to y-axis is now other than the angle psi to preferential distribution. Yeah? Our earlier equation is now valid to the angle to preferential distribution to angle psi. And our angle psi is another, and it's valid from this very trivial picture that psi is alpha plus psi. Yes. So I said our earlier equation is valid also now, but for angle psi. Yeah? And what's valid for now for probability density function? I call it now as a new symbol under the new symbol g psi. It is angle to y-axis, no obligatory to preferential direction. It must be our old function, but with angle psi. Using it, we obtain the final probability density function g psi, which is given by such expression having two parameters. Our known parameter c. This parameter represents generally say the intensity of the preference of this other thing, direction. And parameter alpha, which is angle between two directions, y-axis direction and preferential direction. Well, it was a theory. Now is the question, and how it is in practice. We analyzed using tracer fiber technique, for you maybe known experimental method. We analyzed the curves of fibers in fiber web. It was research for non-woven textiles, and we take a lot of points from this fiber to computer. Then we reconstruct whole curve of fiber in computer. Then we divide our fiber to very small, very short parts. In this picture, it was 0.1 millimeter. And we measured or calculate the angles of orientation, and then we construct the histogram of this distribution. On these two pictures are, in first it is viscose fibers, finally 3.5, in the second 1.7 decitex, and there are such histograms obtained experimentally. When we use our curve and derive using some statistical regression or something, so two parameters, c and alpha, we obtain parameter c 1.84, alpha maybe 2.3 degree, minus 2.3 degree. In the second case 1.97, and the alpha is minus no full 5 degree. Maybe that this angle alpha was the result of experimental error, our mistakes with definition of what is the longitudinal direction. It's very, very small. But you can see that the comparison bring a good results, good correlation with this experiment and theoretical results. We applied our equation for longer fiber segments too. In this case, it is 12.8 millimeter. In this moment, it is empirical application because we derived it for very, very short fiber segments. So that's distribution. You can see that the result is also acceptable. It's also acceptable, but what is interesting, the C is quite harder. C is not then over 4. The question is why? Why it is? How it is possible? It was the same structure, only evaluated for longer fiber segments. How it is possible? It schematically shows this picture. Let's imagine a fiber, a green fiber on our picture, having given shape. In macro trend, we can say it is near to vertical direction. In a short segments, it have a lot of loops and waves and so on and so on. Long fiber segments, the direction of long fiber segments are shown through yellow arrows here. Yeah, you can see that they are near to the longitudinal position, but The short fiber segments, the set of short fiber segments is illustrated through a short red arrows, and you can see that it is not so. Therefore, C for in carding web, the C value for long fiber segments is much more. It's red. Oh, okay. Is much more. Something is wrong. No. The distribution of red arrows is quite other than the distribution of yellow arrows. Yeah? Well, and it is answer why the C is increasing from roughly 2 to value over 4. Sometimes it's necessary to define the probability density function for a non-oriented angle. What I mean, let's imagine some fiber segment. Our angle psi is, or from your side, plus 30 degree or minus 30 degree. There are two different angles psi, plus 30 degree, minus 30 degree, isn't it? But sometimes I want to know how is the distribution of angles between fiber and our y-axis, independent of them if it is on the right hand side or on your left hand side. Yeah. So I need to understand how it is with probability density function of an angle theta, which is absolute value of our angle psi. I think you can more think about this picture. It is also intuitively evident that this probability density function must be sum of two our g functions. One is in angle minus theta, because theta is every time positive. Theta is 30, so for example 30 degree, then minus theta is minus 30 degree, and it's angle psi in minus, plus probability density in plus. Yeah, so that u theta is g minus theta plus g plus theta, which is evident also intuitively. Using our equation, we obtain the final equation in our model as shown. Yeah? Yeah, well, so that's all for probability density function of orientation of fiber segments in fiber assembly. But we often cut our fiber assembly, or by preparation, by praxis in microscopy, the microscopy of textile structures. It's a real section, or some imaginary section by when we use a breaking machine, then the jaw have some line which is something like imaginary section, isn't it? So section is very often. The question is, how is the orientation of fibers, the directional distribution of fibers, but only this fiber segment which are which was cutted. Only this one. Let's think about this problem. Let's imagine some box like this here, full of fibers. This box have the dimensions A, B, C, and a sectional plan is the red plan sigma, this one. The fiber segment number 1, which is shown here, is a special segment which have its endpoints A immediately in the cutting plan alpha. Then the second tenth of such fiber segment is lying in an height h over our sectional plane sigma. Such segment have the length delta L. The angle theta is here, and then h is delta times cosinus theta. It's evident from the picture. Well, same picture is here. How is it now? Let's think about the fibers having angle theta, only having angle theta, no other. There are a lot of fibers inside of our box. Lot of fibers. No all fibers was cut, isn't it? Some other fiber having angle theta, like fiber number 2 or fiber number 3, will not cut it. They are or over or under our sectional plane. The question is, which of fibers, how is the probability that the fiber having angle theta will be cut? Well, let's imagine the parallel plane to our red sectional plane sigma. This blue, which is lying on the distance h from sectional plane. So that the point B of our fiber number 1, fiber segment, I shall say precisely, is lying on our blue plane sigma dash. Yeah? And now, how must be the position of fiber segment when such segment shall be cutted? Now, evidently, the upper point B of such fiber segment must lie between these two planes, sectional plane sigma and our blue plane sigma dash. I think it's evident. So how is the probability of this situation? Using so-called geometrical definition of probability, we can say probability of such section is given by a ratio of two volumes. Volume between our red and blue planes by total volume of our box. Of course, if the fibers are homogeneously distributed in our box. Now, in the case in which all fiber having angle theta are lying near to this corner only by homogeneous distribution. So the probability of section of our fiber segment is ABH by ABC. After rearranging, we obtain this expression. Well, now let's think about fibers having angle theta. All fibers with all angles theta together, all fibers in our box are capital N, and this number is very high. Let's imagine it. U theta is probability density function of angle theta. So that U theta d theta, this U theta d theta, have some logical sense. What is it? It's it's a relative frequency of segments in the elementary class interval of the given angle theta, isn't it? What is it? N times U theta d theta. Relative frequency times total number. It's number of cases in class. You know it also from laboratory and so on. So that N times U theta d theta is number of all segments in elementary class interval on the given angle theta. And now all these fibers was sectioned through our sectional plan, but also some of them. How is the number of cutted fibers? It's total number times probability, isn't it? Times probability. This times this. Using our equation, we obtain this here. It's number of sectioned fiber segments from the group of fibers having angle theta. But the total number of cutted fiber segments is higher, because not only our angle theta exists in our box, also another angles theta are there. Well, so what is total number of cutted fiber segments? It must be integral. Maybe you know that the symbol of integral is from Wilhelm Leibniz, a known mathematician, which started with symbol S. S like Latin sum, summa. And because the S was similar to other A, X, Y, and so on, then he used longer and longer S to today's symbol of integral. So integral is sum, some type of summation, isn't it? So, and we must sum our result over all directions, so that we obtain this here, then this here. It is number of all intersected fibers, evidently. And now probability density fiber, the probability density function of such fibers. Let's call this probability density function U star theta. U star theta. Then U star theta d theta is relative frequency for intersected segments in the elementary class interval of the given angle theta. Isn't it? Well, and what it is valid? What is U theta, U star theta d theta? Relative frequency of such fibers. But in other way, we can say that relative frequency is in class. It is number of fibers in class, our elemental class, Dn, to all fibers, all sectioned fibers. And using our expressions after small rearranging, we obtain this equation, or calling this denominator under symbol Kn, we obtain this formula. Okay? In the moment, Kn is something, is some symbol, no more. But I want to show you that this Kn have some logical sense. Which of? Let's imagine a very short fiber, segment length dl, having a sectional area S star, sectional, in opposite to cross section perpendicular to fiber axis, which is here, and it's S from our earlier lectures. Yeah? The length of this segment is delta L. The height of such segments perpendicular to cutting line is the delta Y. This fiber segment have angle theta. Well, we can write, evidently we can write the volume of such fiber segment. It can be made, it can be used two equivalent methods, I can say. You know it from high school. One is cross section area S times length delta L. The second is sectional area, red shaded, times height delta Y. Both give the same result. Both are here, both the expressions, and from this equivalency, we obtain that S star, this area, S star is this here, so that it S by cosinus theta. Well, evidently, sectional area is larger than cross-sectional area in this case. Well, and now to our symbol. What is it, the mean sectional area? S star bar as a symbol for mean. What is it? Now, as each mean the value S star times relative frequency, means probability density function times differential quantity, and integral. Using this, we obtain this formula here after rearranging this one. And what is here is the integral from probability density function. It must be equal 1, so that it is S by Kn. Resulting equation is that Kn is S by S star bar. It means cross-sectional area of fiber by the mean divided by the mean value of sectional area in our section from all fibers. Yeah. So this is the logical sense of earlier defined Kn coefficient. It will be very important for yarns. Yes, now about the application of our model. It is the equations which we needed. Let's solve the problem. How is the distribution of directions? We have some. Let's imagine we have some, for example, web from black tin fibers, like in our picture here. We make some section. In a planar case, the section is reduced to sectional line. This thick red line is our section. We define the y-axis perpendicular to sections. So this is y-axis, and perpendicular is x-axis, of course. Exists some preferential direction given by blue arrow, and it is interesting for us to derive the probability density function of the short fiber segments which are cut through this sectional line. Yeah. So the distribution of these green arrows, isn't it? Yeah. The distribution of such green arrows which characterize the directions in section of short fiber segments which was sected. Well, how is the strategy of our work? I said sectional plan is reduced now to sectional line. U theta, we derived it in our model. It is this here. It is from earlier slide. U star theta, we derived in this equation, where Kn is this here. So on the position of U theta here and here, we need to use this here and make this integration, which is not too short and formally not too much easy. And when you want to check whole way by integration, and you can use this literature, our literature, and the result you obtain such value of k. It's possible to do analytically, and we obtain this equation for Kn, and then this equation for probability density function of orientation of fiber segments in cutting line in this moment. A note is that if that Kn is by 2 by pi, if for isotropic structure these two are valid. This is the graphical interpretation for our last equations. You can see that there are differences between probability density function of orientation of fiber segments in whole fibrous assembly, U theta, and U star theta, probability density function of distribution of fibers in cutting line. You can see that in these 4 pictures, it's for alpha equals 0, so longitudinal, we cut our web perpendicularly to longitudinal direction. This is for pi by 6, 30 degree, 60 degree, 90 degree. In this example, C equal 1.9 was used, typical value for a web carding event. We can see that the cutting process preference directions near to normal of sectional plane, to perpendicular to sectional plane. Yeah? You can see every time here it is increasing, U star is increasing in relation to U, and the opposite side by 90 degree is decreasing. It's every time going to 0. Also here by alpha equal 30 degree, also here as well as here. Yo? Well, now let us speak about the number of fibers in a section. Number of fibers. Let's imagine something like metal plate on which you have a very thin slot, very long, length C, and very thin delta X, delta H. It's here, yeah? Delta H slot. Slot like here, so that you will not see another fibers. You will see only a fiber segments lying in our very short slot. Yeah. C is length of the slot, delta H thickness of slot, N is number of all intersected fibers. Intersected because I can use my knife and make this section really, isn't it? Yeah. Number of all intersection fibers. I is subscript for fibers from this green fiber segments from 1 to N. G is mass per unit area, known as areal weight in industry. Raw fiber density. SI star is a sectional area of per one fiber. For example, if height fiber is this one, so this here, and it is S by cosinus of corresponding angle theta I angle. Yeah. How is the mass of height fiber segment? Height fiber segment have the mass cross section area times perpendicular height, its volume times raw mass density. Now this is the mass per one fiber. Mass per all fibers in our slot is sum of them. So it is delta M, which is sum of this. Because delta H as well as rho are constant, it's possible to write it in such form, isn't it? The total area of slim slot is C length times delta H. And then the mass per unit area of a planar fiber assembly is G, which is mass by area. No, okay, for delta M we have this expression, C times delta H stay here. Delta H is here as well as in denominator, so that I can write this black relation. But nevertheless, I can multiply and divide by N, total number of fibers in our slot. It's possible. How is the sense of our the mathematical structures now? What is it? N by C, number of our earlier green fibers by C. It's number of fibers per unit length of our section on our slot, isn't it? And total number by C. Rho, what is this here? Sum of all fiber sections divided by number of fibers. No, it's mean value. It's S star bar, isn't it? Mean value of sectional plan. So that new number of sectioned fibers per unit length and S bar star mean sectional area of fibers, there are symbols. The new is G by rho times S star bar. yeah, nu times rho times S star bar, so that from this nu is this here. So we can multiply it and divide by S. We obtain these structures, but T is S times rho. It is from first lecture. You know from our first lecture that T is S times rho. Fiber fineness is fiber cross-section times specific mass. This is this one, and S by S star bar, it was Kn. So that we can write that the new number of section fibers per unit length is fiber mass per unit area by fiber fineness times the coefficient Kn. Yeah? The node need depends, of course, of alpha. It means to the angle in which we cut in relation to referential angle. Why it is commented here, yeah. The intersection method is one method which is possible to use for experimental evaluation of distribution of fiber directions. It is a special method which based on our equations, and it is possible to do it in laboratory, although it is not too easy, I must say. When you want, you can study this way in my lectures. We will not comment it today. I only want to say how is the experimental background of such method. You need to measure number of cross-section fibers, maybe optically or something so, in different directions in our web. When you know when you have the set of experimental obtained values for different alpha, you can from this set of experimental data to evaluate the u theta probability density function of directions of our fiber segments. It is this here, and here is also an example which documented the correspondence our model and experimental research from another authors is well. Now stop of this lecture, and in a following lecture we will continue with a topic how to apply our knowledge about fiber orientation to a mechanical behavior. So thank you for your attention.